Okay, so we are going to talk today about chapter 4. Starting with chapter 4. So we're going to talk for about 6 or 7 slides in chapter 4. Then we're going to go off the grid and talk a little bit more about the quantum model of the atom, which I don't feel like this chapter gives enough credit to or covers enough. So I just want to make sure that you guys have an understanding of exactly what the theory is right now before we get more into the electron levels and the energy levels in the Bohr model. So that being said, the whole point of this chapter is all about really electrons. And electrons are the superstars of chemistry. You all know that protons are important because that lets you know what the atom actually is. The number of protons determines the identity of the element. But the electrons are so important because they are the parts of the atom that are moving. This is what forms and breaks bonds. The electrons are where we see energy being absorbed and released. And so that is what we're going to talk about in this chapter. If we look at the picture on the slide, it's a picture of, obviously, traffic in a city. Now, why is it blurry? They are moving. Yes, if you had to pinpoint the exact location of one of the vehicles in this photo, would that be difficult to do? Yes. So this is kind of how we see electrons. Because they are moving at such a fast rate, and the ability that we have to look at them is very limited. Whenever we see an electron, it looks something like this. We are going to talk today about the fact that an electron is a particle and it's a wave. This is called duality, electron-particle duality. Electron-particle duality, where you have it's a particle and it's a wave. In the early 1920s, there were two definite schools of thought. We had people who were like, the electron, it's a particle, it has mass. And the other thought, or the other group, was the electron, it's a wave, it moves in a certain way. Both of those had to come together to figure out what an electron actually is and how it behaves. And that is one of the things that we're going to talk about today. Flicker. I swear it hates me. All right, so starting with the wave nature of light. This is something we did not hit very much last year in Honors Chem, and I'm going to make sure that we hit it in ACP. I'm also hitting it in Honors Chem a little harder this year because there is more of it in ACP. So what is light? Light is a form of matter or energy. Energy, yes, very good. The part of the electromagnetic spectrum of light that we can see is very, very narrow. It is just this little bitty spot right here. So our eyes, the human eyes, can really only see about 400 nanometers to 700 nanometers wavelength. The rest of the spectrum we are unable to visibly see. But those waves on the spectrum are still out there. Going all the way from radio waves on the low energy, long wavelength end to gamma rays, which are rays that come off of nuclear, when we have a nuclear reaction, that are very, very high energy, high frequency waves. All of those waves are part of this electromagnetic spectrum. Now, this is a continuum of energies from the highest energy all the way to the lowest energy. And the thing about this energy spectrum, what I'm going to tell you now, is that gamma rays are the smallest frequency, or the smallest wavelength waves that we have. I anticipate that at some point in time, we will be able to detect something on the other side of this, like even smaller than the gamma rays. At this point, we haven't, but I think that eventually there will be something else there. There are indicators that this continuum continues farther out than what we can see right now. So the different regions represent different types of light. So we have gamma rays, which are given off when we have a nuclear reaction. We have X-rays. You all know what those are. We use those typically to detect broken bones. I don't know if it talked about it in your book, but the discovery of X-rays killed the people that did discover them because they are radioactive and they will kill you if you're exposed too much. That's why they cover you very nicely, typically, and then they go and they stand behind the little wall so that they're not exposed, right? That is an X-ray. Small doses of this you're okay with, but if you happen to be an X-ray technician and you didn't like protect yourself day after day after day after day, that would cause it would cause cancer, and it would cause different changes in your genetic code, which would cause you to no longer be alive. Ultraviolet light are the type of light that gives you a sunburn. You can't see it, but it does burn your skin. That's the type of light given off by the sun that affects your skin adversely. Infrared light is the type of light that we can't see, but like maybe in the movies you've seen where the guys wear the infrared goggles and you're able to see the heat spots in a building, like where people are and things like that. Or the infrared images of different types of animals. You can see like there, it's a heat signature. Microwave, obviously, is in this little space here, and radio waves are the farthest out. Now, typically when we hear radio, we think like AM, FM, but I also want you to think like ham radio, CB radio. There's other, you guys know what a CB is, right?
No.
Oh my gosh. You know, like have you ever seen an old movie that has like a truck driver and they're like, 10-4, good buddy, breaker, breaker, and they've got like the little box in their car and it has like a squiggly thing and it comes up to a microphone where you push the button and you can like, that's a CB radio. So people used to have them in their car before there was such a thing as cell phones. Yeah, and like police officers use a radio instead of a cell phone. Bus drivers have the radios in the buses where they can call into the office. Yeah. So used for communication. Yes. Oh my goodness. I'm old. Okay. You threw me off. Sorry. I'm going to be the first to admit that I am like the mean mom. I was so concerned about microwaves because my mom had me convinced that microwaves were dangerous. That I wouldn't even let my kids stand in front of the microwave and watch their food because I was worried that it was going to be dangerous for them. And they were absolutely positively not allowed to open the microwave while it was still running. You had to hit the stop button and then open it. That is not true. Microwaves are not dangerous to you outside of the microwave. Now, if you happen to be inside the microwave and someone turned it on, that's a different story, but it's not because of the microwaves. It's because those microwaves would heat up the water in your body and cause it to boil, and that is problematic to a human. Okay, so when we're looking at wavelengths, I can't remember. Okay, let's talk about the visible spectrum to the human eye. So the visible spectrum that we can see in the human eye, we can only see from 400 nanometers to approximately 700 nanometers. The visible spectrum is the Roy G. Biv color. Starting, the red is at the 700 end, and the purple is at the, violet is at the 400 nanometer spectrum. Now, because we're people and every person is different, there are slight variations in that amount of visible light that different people can see, but it isn't a lot. Also, just a side note, to be able to see the color, it has to be reflected back to you. So, like, if you've ever been in a dark room and you're looking at someone, and it's pretty dark, but it's not, like, completely dark, so you can kind of still see them. Like, if you said, well, what color shirt did they have on? Like, they had on a red shirt, but when you're in a really dark room, it might look to like gray or black, right? It's because it's not reflecting back to you. So when you turn the lights on and it hits that color and reflects back to your eyes, that's when you can see it. So the cool thing is, any light moving at 400 nanometers is violet. Any light moving at 700 nanometers is red. That's the cool thing. Yeah.
How does glow in the dark work?
Glow in the dark.
Yeah.
It is giving off its own light. So it's not a reflection. Does that make sense?
Yeah.
Yeah. So depending on what wavelength is coming off of that color, it's going to be a different color.
All right.
Yeah. So like the red glow is going to be like your 700. It's still the same. It's just it is actually its own light source. And last year when we did the flame test and you guys would test the different metals and you see the different colors, you were able to see what those metals reflected, what kind of light they reflected. Okay, so if we look at the nature of a wave, we've got a couple different things that I want to make sure you understand. Number one is this is called a lambda, and the lambda stands for wavelength. We are measuring from crest to crest, or you can measure from trough to trough. As long as you are measuring at the same point on each wave, that's what we're looking at, is the length of the space between waves. So in this instance, we have red light, which is always at 700 nanometers, violet light, which is 400 nanometers. Now, which of these has a shorter wavelength, George? The violet light has a shorter wavelength. The other thing we need to talk about is frequency. So frequency is measured in the amount of waves that go past a certain point in a set period of time. Typically, we look at it in a second. So we would watch a certain spot for 1 second and how many waves went by in that amount of time. Remembering that all light is still traveling at 3.0 times 10 to the 8th meters per second. All light is traveling at that speed. We're not talking about that. It's all moving at that speed. The question is, how many times is it going up and down at that speed in that spot? So imagine you're like riding on a car, or you're driving in a car, and one person is going up and down like this, right? And another person sitting beside them or standing beside them is moving at a faster rate. You're both still traveling at whatever speed the car is going. But one person is going up and down at a slower rate while the other one is going quicker. That's what frequency is looking at. So if we look at that, which of these has a higher frequency, the red or the violet? The violet, yeah. So the violet has a higher frequency. So wavelength and frequency are inversely proportional. The shorter the wavelength, the higher the frequency, right? So look at your red. It has a longer wavelength and a lower frequency. This frequency also corresponds directly to energy, because it's going to take more energy to go up and down more times in a certain period of time, right? So the higher the frequency, the higher the energy, which takes us back to our electromagnetic spectrum. We've got super high energy on one end, where we've got high frequency and short wavelength, and lower energy, lower frequency, and a longer wavelength on that. And when I'm talking about wavelengths, I'm talking about, like, on this end, we're in like the like super nanometers, teeny tiny little spaces over here. And on this end, like, the radio wavelengths are like anywhere from 3 to 30 meters long. So this is a large gamut of wavelengths that we're looking at. Anybody got questions on that? Yes? No? Okay, here we go. All right, so the equation that we are going to use to talk about the nature of light, or the wave nature of light, is E equals Planck's constant times the speed of light over h. So I forgot to turn on my annotate thing. Hold on a second. Is it here? Nope. How about here? There we go. Oh, come on. Sorry. Okay. Yes, please. So E. Why? Why does it think I want this? Just thank you. All right. E is energy. Oh my goodness. H is Planck's constant, Planck's. I'm not sure if you guys wrote this down. This is 3.626 times 10 to the negative 34th. If this looks familiar, it should, because we talked about this on a bonus question from last time. C is your speed of light. .3 times 10 to the 8th. This is in meters per second. This Planck's constant is in joules times second. And the lambda right here is your wavelength. This number, this wavelength, needs to be in meters. So a lot of times they will give you your wavelength in nanometers. You're going to have to convert it. Remembering that 1 meter equals 1 times 10 to the 9th nanometers. Okay? All right. So now, what is the energy of blue light that has a wavelength of 450 nanometers? So you need to solve for energy equals H times C over wavelength in meters. Let's see what you got. Yeah.
But we need to remember those numbers for Planck's.
No, they are on your sheet on the exam. And then I think they're on the sheet on the practice exam I gave you too. All of that stuff that's on there you will get. You don't have to memorize the equation or the constants. Yeah, I think the sheet, I printed your test already.
It's on the practice.
Yeah, it's on. That stuff's on there. Yep. I'm going to write the answer up here so that you guys can confirm that you get it right.
So basically every time it's 34 times
Speed of light.
0
Mm-hmm.
over whatever.
Mm-hmm. Punch it in and make sure you get the right answer. She said, yeah. She said, no. Yours says the negative 18.
That's a 9.
That is not a 9. You are a liar.
Why did you do it?
Did you hit 10 E? It's supposed to be 1 E. Yeah. No. Yep. This is joules times seconds, right? And this one is. This is joules times seconds, right? And then this one is meters per second. So your seconds are going to cancel. And then when you divide by your wavelength, your meters cancel out, so you should be in joules. You guys convert your wavelength to nanometers. Yeah. Uh-huh.
What's nanometers?
Yes.
Because it says 4.5 again. You have to pick a speed.
It says 450 nanometers.
It's a meter.
Yes.
What?
So it's 4.5 meters.
Yes. Did you get it?
What was we saying?
Because 34 plus 8 should be 26.
Are you still not?
25 minus negative 7 should give you 19. It's not a negative 7.
I think that's okay.
Yes, it is. No, it's a negative 7. It should be the negative 25th, right? Did you put it in negative 34? Negative 34 plus 8 should give you the negative.
26. Did you get 2.31?
Yeah, that's what I keep
That's
getting.
what I got.
Yeah, I keep getting
like
2.4.
2.4.
What'd you get?
I keep getting 2.4.
I keep getting 2.4
Did I write the wrong answer?
I got the right answer.
I got, what's the answer?
I'm not
I wrote it
gonna
up there.
get the right answer.
So this is wrong.
It's 4.5 to the.
6.626
We got
e to the negative 34.
Isn't it 3.6?
Six.
What?
It's
six.
She said
6.626.
Wait, what's playing?
I got that
That's what it
right.
said in my bag.
She said.
6.626. Did I say the wrong thing?
Yeah,
You
it
said
said
three.
said 3.
Oh,
Wait, what she?
what?
She said 0.9.
No.
So I had
You
it
said it was
like before.
3.6.
Sorry. Planck's constant equals 6.626 times 10 to the negative 34.
Mrs. Jackson.
Yeah.
I have that answer, but I have it down like, I have it as 0.044173 times 10 to the 17th.
That is not correct scientific notation for one thing. Remember, scientific notation is
Yes.
always
Okay.
one number, and then so you have to move it 2 spaces, which would make it
4.42.
right.
I got it now.
It's 7 or negative?
Did you figure it out? Right.
Negative 25 times that.
What are you getting that finger now?
So she's taking it. That's how I got it.
Did you get 3.0?
So it's 4.5 times 10. Something.
That's why I know.
Or negative.
I still got it wrong. This is 4.22.
Oh, well, you're telling your calculator to, when you write it in like this, your calculator divides this by this and then multiplies it. So you guys have, you either have to put parentheses around the whole thing to start.
He's getting 4. At least he's got one. 4.47. I'm not cold. I doubt I'll get cold. I'm no longer in foster.
This girl's always very fine. It's the ones that are like
Oh, I said my mind.
Each one there gotta be something input here.
My eyes are reading, not my eyes.
So what are you reading?
Or maybe parentheses. How are we, Zach? Did you get
Josh,
anything
your
good?
handwriting is a little too small.
Izzy, are you good? Haley?
Yeah.
Good,
Mine's worse than his.
good, okay. Do the next one.
Oh.
Oh my god.
You go. Let's see you do it.
Grabbing the calculator.
Go.
Wavelength. Oh, I actually have to write this one down. Maybe, I don't know.
Okay, I got
I
mine.
got.
Yes.
So what is the one? What's the energy system? First one.
60.
This is reacting. I keep getting this one. It's
How
all
did you get
5.2.
that?
I did the math.
Wait, is it nanometers? Is mine in nanometers?
Maybe.
Yes, it is.
You still didn't put the whole thing in parentheses. Oh, no, you did that time. Because it wasn't 4.7.
Gosh.
Yeah, I'm getting the right answer with the wrong.
because
and then
I was trying to figure out this. I still
no,
have
around
to
the
figure it out.
yeah.
I'll just pull the whole thing over.
When you're done, you're done.
I can ask questions tomorrow.
I'm speaking of this.
Yes.
And I can back this. You know, right? Like, you divide these.
Not a negative, like you divide.
Yeah.
On the board. My glasses cannot aid me. in
Where's your
dividing.
negative 0.6?
My glasses are very old.
Well, I didn't do that yet. So what I do is I do numbers and then I do.
Okay, that's fine. So you got 0.176. 0.176. So
I
negative
got the first
0.6 minus.
Will be negative 19 minus.
Because- Is it? And the second one. That's a negative 19.
Yeah.
Oh, yeah.
Why do you have the 19 on the bottom?
Oh, that's true.
Because I'm dividing both sides by.
That wouldn't give you that. You have to divide this. You have to like here. You have to divide that goes to the bottom.
How do I know what this equals? Or wait, so I would do mine to be, I multiply that by both sides and then divide that by
Yes,
that.
yes,
Okay,
yes,
I
yes.
got you.
It's so refreshing to have someone see that. Thank you. How are we doing? We good over here?
I'll watch this.
Okay, perfect. Can you go over and look at Ryan's calculator?
Where do you get nanometer from?
I think yours with you.
Right?
Yeah. Because it's so. You're laughing.
Aren't you excited to read that? You read it now, tell me what your opinion before I write it all down in pen and categorize it. Yeah, but they give you have to find a way.
Not in my bag.
It's still wrong?
Yeah.
Okay. Look. So you are writing E equals H times C over wavelength, right? So you're solving for this. Yes? So if I was doing it, I would multiply both sides by wavelength. That cancels those out, right? So now I have H times C equals E times lambda. Yeah? Now divide both sides by energy. So that cancels that out. So I'm going to rewrite this. It's just lambda equals H times C over my energy. And then all you have to do is plug your numbers in. Because you know Planck's constant, you know the speed of light, and it gives you your energy here. Yep. Did you get it figured out? Okay, good. Thank you, Josh. Okay, we're going to stop on this. We can come back to it, but I want to get to this part about the quantum model here. Okay, so we're going to talk a lot about Bohr's model. And while Bohr's model is effective to use as a model, I want to make sure that you guys understand what the actual quantum model looks like and what chemistry and what the science actually believes right now. So Bohr's model is mathematically and hypothetically supported. It's supported in experiments as long as there is only one electron on the atom. So how many of those elements is that going to work for? One. It doesn't work once they started applying it to all the other elements on the periodic table. So it's like, wait a second. How? Why? How is this working? Why is it not working? So here are the main players of, you don't have to memorize any of these guys, but here, I just want to give some creds and tell you what's going on here. Niels Bohr and Werner Heisenberger were on team electron is a particle. They were saying, no, it has mass. We know, we can see, it is a particle. It is composed of matter. On the other side, we have de Broglie and Schrodinger, who are adamant. No, the electron is a wave. It's acting as a wave. So these two camps of people were basically working towards the understanding that in 1924, de Broglie proposed this revolutionary idea that changed the entire idea. And that was, he said that an electron has wave-like properties. It acts like a wave. It is a particle. We know it has mass. It's made of matter, but it acts like a wave. And so he used Bohr, Planck, Einstein's work. He put it all together, and he said that electrons should be considered waves that are confined to a space around the nucleus. Looks something like this. It was a brand new idea. It was like one of those ideas that like shatters the glass ceiling. Brand new idea. And then in 1926, Erwin Schrodinger developed the equation. And this equation treats electrons as waves. And it gives you an idea of how they were acting. So he put it all together. He talked about the quantization. He talked about the energy. He talked about the frequency. And he was able to experimentally prove that this equation works. This tells you how electrons act. You don't have to memorize this. You don't have to be able to use it. I want you to see it. This is Schrodinger's equation that tells us about the wave-particle action of electrons. So we put this all together, and so which is it? Is it a particle? Is it a wave? 1927, Heisenberg suggested, this guy is a physicist and a philosopher. He suggested that it's impossible to know exactly where an electron is located at all times. He calls this the Heisenberg uncertainty principle. Here's the thing. If we pinpoint the location of the electron, we cannot see its wave properties. If we know the speed and the wave pattern that the electron is moving at, we cannot say where it's located. We cannot pinpoint the location. So it's impossible to know both at the same time. You can't know the position and the speed. You can know the position or you can know the speed, but we can't see them both at the same time. So think of it like this. This is the best example I've ever seen. When you have a fan and you can see the fan blades, you know exactly where they're located, right? You can see them. They're in the position. Once that fan starts to move, we can't tell with certainty at any time where the blades are. You can't say at an exact time where it is. It looks like a blur. This is what the electron cloud looks like. They're moving around very, very quickly. But we can use math to say this. We know that those blades are here, and we know for sure that they are not out here. They're not out in this space. We know that they're in this space somewhere. They are not outside of that space. So that is the Heisenberg uncertainty principle. We can either stop it and look at it and see exactly where it is, or we can tell you the speed of the fan or the speed that it's moving, but we can't tell you exactly where that blade is at 1 nanosecond in time. So that is how the quantum model works. It's not the nice little rings around the nucleus that you got taught in 8th grade. That's not how that works. It works like this. So all together, we determined that the electron is a particle that moves as a wave in specific spaces around the nucleus. It's only found in certain places. So our current model of the atom is the quantum mechanical model. So I wanted to go into detail with you on that, mostly because my honors chemistry kids are about ready to make me pull my hair out. They're like, yeah, but 2s2 and 2p6, we thought there was 8 electrons around the nucleus. And I'm like, oh my gosh. Okay. Everything that you learned before is just a model. So this is the same idea. The Bohr model, all of that, we learned how to put all and where our electrons are. It's all a mathematical probability that we think it's in that space. And that's our idea. Okay, you guys got any questions for me? Yeah? No? Okay. We got like 5 minutes of work waiting. We're done for the day. There is group work in your folder that at some point I would like you to take a look at. I'm going to change that. You should be able to do the first 2 or 3 problems already, I think. And I'm going to change that date in Schoology.